All right. Chapter 2. We're going to move on to Chapter 2. So our first lesson in our LLM University, we did what were sentence and word embeddings. And now we are moving on to what is similarity between sentences. Similar to the embeddings, how are they characterized? What numbers are they given? You'll see those numbers come into play and where they're plotted on these three-dimensional area graphs per se, right? In vacant space to see where they're located in relativity to one another. For large language models, it is crucial to know when two words or two sentences are similar or different. This can be a hard problem, but luckily word and sentence embeddings are very helpful for this task. In this post, we go over some different notions of similarity. For large language models, it is crucial to know when two words or two sentences are similar or different. This can be a hard problem, but luckily word and sentence embeddings are very helpful for this task. In this chapter, we go over some different notions of similarity. Similarity between text. Knowing if two words are similar or different is a very important task for every large language model. An even harder problem is knowing if two different sentences are similar or different. But luckily, word and sentence embeddings are very useful for this task. In the previous chapter, I explained the concept of word embeddings. In a nutshell, a word embedding is an assignment of a list of numbers, otherwise known as a vector, to every word. Remember or recall that each word or sentence is given a set of numbers that correspond or correlate to a given category to help the LLM conceptualize or store this word or sentence. So for example, if you were doing giraffe, it might have a 9 for height, it might have a 4 for color, and so forth. In a nutshell, those word embeddings are a list of numbers to every word in a way that the semantic properties of the word translate into mathematical properties of the numbers. What do we mean by this? For example, two similar words will have similar vectors, and two different words will have different vectors, but most importantly, each entry in the vector corresponds to a word that keeps track of some property of the word. Some of these properties can be understandable to humans, such as age, size, gender, but some others could potentially also only be understood by the computer. Either way, we can benefit from these embeddings immensely for many useful tasks. Sentence embeddings are even more powerful as they assign a vector of numbers, remember vector being a large amount of numbers, so many different numbers. They assign a vector of numbers to each sentence in a way that these numbers also carry important properties of the sentence. One of the cohere embeddings assign a vector of length 4096, or otherwise 4000 different numbers or categories assigned to each sentence. Furthermore, multilingual embedding does this for sentences in more than 100 languages. So it embeds thousands upon thousands of sentences in English, but then does this across 100 of languages. And so you can start to see how this might stack upon one another, where you could communicate amongst different crowds, hundreds of different languages, while this AI is extrapolating or understanding the meaning behind these words and sentences so that there is less translation lost, right? There's some words that may not be in other languages, but the AI knowing these embeddings and knowing how they correlate to one another in this three-dimensional space, in this plot, could help people communicate in a way that we haven't been able to before, right? We can start to discuss things in multiple languages without that loss in translation. In this way, the sentence, hello, how are you, and its corresponding French translation, bonjour, comment ça va, will be assigned very similar numbers as they have the same semantic meaning. Okay, so in this graph, in this 3D plot cube area, they would be clustered close to one another, even though they're in different languages. Now that we know embeddings quite well, let's move on to using them to find similarities. There are two types of similarities we'll define in this post: dot product similarity or cosine similarity. Two types of similarities we'll define in this post: dot product similarity and cosine similarity. Both are very similar and very useful to determine if two words or sentences are similar. Let's start with a small example of sentence embedding for dot product similarity. For simplicity, let's consider a data set of 4 sentences, all movie titles, and an embedding of dimension 2, meaning that each sentence is assigned 2 numbers. Let's say that the embedding is the following. For those that aren't watching, You've Got Mail with 0 and 5, Rush Hour at 6 and 5, Rush Hour 2 at 7 and 4, and Taken at 7 and 0. If we take a closer look at these scores, would they mean anything? What would you find? Well, as mentioned before, these scores sometimes mean something that humans can understand, and other times they don't. But in this case, you notice that the first score is 0 for You've Got Mail, but high for all other movies. If you've seen these movies, is there anything that you could think of or any feature that these 3 movies might have different from You've Got Mail? The author could think of one. It's being an action movie. The second score is high for You've Got Mail, Rush Hour, and Rush Hour 2, but low for Taken. And what could that property be? It could be that it's comedy, right? So on the left, if we go down vertically, You've Got Mail is 0, but Rush Hour 1s and 2 are 6 and 7. That's the left-hand side. That is the action category. Then the right side, with Taken being a 0, it's not a funny movie at all, and the others having 4s and 5s, you can see that that's kind of a comedy, right? Rush Hour 2's got some comedy to it. Therefore, in our embedding, it could well be that the first score is the amount of action in the movie, and the second score is the amount of comedy. And they've broken this out into a table for us to see score 1, which being action, score 2 being comedy, and you can kind of assume where this would be placed on a movie genre graph. Now imagine that we want to find the similarities between these movies. In particular, how similar would you say that Taken is from You've Got Mail? How similar is Rush Hour to Rush Hour 2? Right, one's prequel, one's a sequel. In my opinion, Taken and You've Got Mail are very different, but Rush Hour 2 are very similar, and we now need to create a similarity score to show that. Here is one way to create the similarity score. If 2 movies are similar, then they must have similar action scores and similar comedy scores, right? Action being that left column, right being the comedy. So if we multiply the 2 action scores, then multiply the 2 comedy scores, and add them, this number would be high if the scores match. On the other hand, if the scores don't match very well, right, if there's 0 times anything is 0, the similarity score would be lower. This operation is called the dot product, right? So for You've Got Mail and Taken, You've Got Mail was a 0 for action and Taken was a 7, so 0 times 7 is 0. And then for comedy, You've Got Mail was a 5 and Taken was a 0, so also 0. So 0 plus 0 is 0, meaning that these are not similar whatsoever. But if we do the same for Rush Hour and Rush Hour 2, 6 times 7 plus 5 times 4 is 62. The higher that number is, the more similar they are because that is a similarity score. And this matches our intuition since we were expecting a low similarity for the first pair and a high similarity for the second pair. Cosine similarity. So we had dot similarity, now we've got cosine similarity. Okay? Cosine similarity is another measure of similarity between sentences and words. Is to look at the angle between them. Break out your sine, cosine, tangent, cosine similarity. See, it's coming together, right? For example, let's plot the movie embedding in the plane. These are the movies we just talked about, where the horizontal axis represents the action score and the vertical axis represents the comedy score. And the embeddings might look something like this, where these same numbers that we were given before just planted on a 2-dimensional graph. Top left corner at 5, You've Got Mail. Bottom right corner at 7 is Taken. Notice that You've Got Mail is quite far from Taken, which makes sense since they are very different movies. And furthermore, Rush Hour 2 are very close. We know they're in the same family. So Euclidean distance is the length of the line between 2 points is a good measure of similarity. We need to tweak it a little bit since we want a measure of similarity that is high for sentences that are close to each other and low for sentences that are far away from each other. Again, this is that similarity. The higher the similarity rating, the closer they are in similarity and vice versa. Distance does the exact opposite. So in order to treat, In order to tweak that metric of distance being the measure, right? So the bigger the distance number, the less similar they would be. And the shorter the distance, the more similar they would be, but that's kind of counterintuitive. We want the higher the number, the more similar. So in order to tweak this a little bit, we look at the angle between the rays from the origin, the point where the coordinates are 0, 0, and each sentence. Notice that this angle is small if the points are close to each other, right? So if we have a point here and a point here, okay, how do I stack that? Okay, and then we have a point on the left. Think of it as a triangle. We're making a triangle. The smaller the angle between the two, the closer they are. But the wider the angle, the more that distance grows, the farther they are. And then we'll incorporate cosine to give us the inverse. So notice that this angle is small if the points are close to each other and large if the points are far away from each other. Now we need the help of another function, the cosine. So recall back to, what is this, like middle school geography? I don't know. You wonder where you use cosine, tangent, all this fun stuff. Pythagorean theorem. Don't use it in the day-to-day, but here it is again. So refresh those training wheels. The cosine of angles close to 0 is close to 1, and as the angle grows, the cosine decreases. This is exactly what we need. Therefore, we define the cosine distance as the cosine of the angle formed by the two rays going from the origin to the two sentences. So on the left, you can see our highly dissimilar movies. You've got Male and Taken. You can see they form a right angle because You've Got Mail is a 0 for comedy and Taken is a 0 for action. So the bottom x-axis is action and the vertical is comedy. Being a 90-degree angle, the cosine is 0. Okay, so they are not similar at all. Whereas if we do for Rush Hour 2, we can see that that cosine is 0.98, right? It is very, very close to 1, meaning that they are very similar. And so we can see how the cosine can be used using the distance essentially to see how similar and dissimilar movies or sentences can be. They do provide real life examples in these trainings, providing code for us to run our own for us to write our own process, but I don't think we're going to go through that just so people can see what that code looks like, and we're not going to take this out to actually run those tests. I don't know if we need API keys. I don't really want to go through running this because we can see how it works, and we don't need the data that's provided. But what we'll see from the results is that it's provided a list or a vector of numbers. We can see in this bottom result the embeddings for the sentences 1, 2, and 3. And those sentences were, I like to be in my house. I enjoy staying home. The isotope 238U decays to 206 PB. And looking at those texts, those 3 sentences, we can see that the third one has nothing to do with the first 2. The third one is about radioactive isotopes, and the first 2 is about staying home in your house. And so if we go down to these vectors that this produced, this 1024 number vector, we can see that the numbers that were given to these sentences by the AI model. And these embeddings are truncated, right, because there's 1,000. And so there's only a few in this result set. And so we can't really see if there's anything that, is popping out of those 1,000 numbers, right? We only have 5. But one would expect that the vectors 1 and 2 are similar, as we just said that they're related to staying in a house. While 3 is different in that it's talking about radioactive isotopes. However, from inspection, this is not very clear. We need to calculate some of these similarities to see if this is the case, right? You and I can see that it's different, but the AI is not going to be able to read that context if it's not embedding those words. So this article goes on to use that dot product similarity that we talked about before, where it's going to take the number from the left, or the number from the first column, okay? It's going to take the number from the first column from the second sentence. So we have the first column, first sentence, first column, second sentence. We're going to multiply them, and we're going to do that for all those embeddings and add it up. The good thing about machines and AI is that it can do all these calculations for us. We don't need to write these down on paper. So it's going to do that dot similarity, that dot product similarity for 1 verse 2, 2 verse 3, and the 1 verse 3, so that we have all the similarities that we see. And the results are, as you expect, the following. The similarity between 1 and 2, sentences 1 and 2, which were I like to be in my house and I enjoy staying home. The similarity dot product score was 0.818. So nearly 81% similar, 82% similar if we're rounding up. But if we look at those two sentences of I like to be in my house and I enjoy staying home, if we take those two sentences and we do the dot product of the similarity versus the isotope 238U, we can see that they both come out to roughly 20% similar. That is not high in the grand scheme of things, but we'll continue. So the similarity between 1 and 2 is much larger than the similarities between the other two pairs. And just for consistency, we can also calculate the similarities between each sentence and itself to confirm that a sentence and itself has the highest similarity score. Sentence 1 verse 1 is rounding up 100%, and the other two are 100%, actually over 100%, a little bit. This checks out the similarity between a sentence and itself is around 1, which is higher than all the other similarities. Now let's calculate the cosine similarities between them. Again, it's taking that cosine form, and this is just showing us what it looks like, what the AI is actually going to run code-wise. So if we start from the top, we are importing a few packages. Then we are using the Cohere module to create a AI client. Right, you need that API key. You need they give you the free API key. It's exactly why I didn't want to go into this. We are then writing the code to print the embeddings. We got the embeddings. We went over that. And then now it is doing the dot product, right? Print the dot product where it's doing the dot. It's multiplying each other. And then to where we are now with cosine similarity, it is going to, we are printing the phrase cosine similarity between sentences X and Y. And then we are running this function called cosine similarity, sentence 1 versus sentence 2, and then creating two arrays. So the cosine similarity, skipping all that jargon, we're going straight to the results. The cosine similarity between sentences 1 and 2, again, is 82%, and the other two is 20%. So if we check the similarity, the cosine similarity versus sentences themselves, we get the same exact result, 100%. Sentence is going to match to itself. So we see that the cosine and the dot product similarities are going to give us nearly the exact same results. While the numbers may slightly differ, the context, the outcome is exactly the same. And we can see this plotted on a graph. We can see that the cosine similarity or the dot product similarity are giving us these similarity ratings, these percentages of how closely these three sentences are related to one another. Okay, the lighter the color is means the closer it is similar to one another. And so I like to be in my house, right? Very light, looks like a light blue there, is going to be 100% correlated to, you guessed it, the same sentence, I like to be in my house, this top left corner here. But I like to be in my house is similar to I enjoy staying home. And we can see that that color kind of situates in that 80% range. And if we go farther down in the bottom left corner, we have a dark blue, which is the isotope 238U, that whole decay thing. So I like to be in my house has very little similarity to nuclear decay. The similarity between each sentence and itself is 1, which is consistent with our expectations. Furthermore, a sentence and itself represent the same point in space, which gives an angle of 0 with the origin, so it makes sense that the similarity is the cosine of 0, which is 1. Figure. Go figure. Middle school geometry. Notice that the dot product and the cosine distance give nearly identical values, although not exact. The reason for this is that the embedding is normalized, meaning each vector has norm equal to 1. When the embedding is not normalized, the dot product and cosine distance would give different values. Conclusion. In the previous chapter, we learned that sentence embeddings are the bread and butter of language models, as they associate each sentence with a particular list of numbers, a vector, in a way that similar sentences give similar vectors. We can think of embeddings as a way to locate each sentence in space in a way that similar sentences are located close by. Once we have each sentence somewhere in space, it's natural to think of distances between them. An even more intuitive way to think of distance is to think of similarities, i.e., a score assigned to each pair of sentences, which is high when these sentences are similar and low when they are different. The similarity is a very useful concept in large language models, as it can be used for search, for translation, for summarization, and in many other applications. To learn more about these applications, stay tuned for our next stream. So I want to point out something real quick, in that you can do this, or that humans do this with anything, right? If you're a teacher and you have a group of kids in your classroom and you wanted to divide these kids up into groups, but you wanted to make sure that these groups had something in common so that they weren't stuck not talking to each other, you would find a way to group these kids, whether it be by subjects, sports, height, gender, you name it. And you would essentially plot these kids on a graph to find what similarities they have to make a further decision. And that is exactly what these AIs are doing. They are plotting these sentences on a graph and grouping them with similarities so that when it needs to recall or use later on in the future, use these sentences, it knows where it can go grab them. And it's a little puzzling to us as humans with humans cognition or human cognition, that we can assign a number not only to words but to this whole sentences themselves. Is kind of mind-boggling to us, because when we recall words and we recall sentences, we're not thinking, okay, 8 means what, 12 is it doesn't work like that. But a machine only thinks in zeros and ones, these numbers, and because we have to translate these words into machine ingestible language, we're translating that and assigning numbers to it. And because we have now translated something, a verbal language, into a machine readable language in a way that it has to translate the basic understandings of these words and sentences, we can come up, or it might be able to come up with new ways that we are able to understand or piece together words and sentences. And so we are still in, I don't want to say it's infancy. AI has come a long way, but there's still some nuances to this, right? It might couple certain words together, or slang. AI doesn't fully interpret the meaning of slang, or even some memes, right? It doesn't have those contexts. If it can't understand pictures, it won't understand a meme, even if you give it the words in the meme. And so there's a lot of mimetic things that humans have created that machines don't fully understand yet. They don't understand the little nuances to our language. They only understand the verbatim of our language. But over time, it will start to learn what those means, right? Like if you say, hey, I like this movie, sarcastically, if you're not verbally saying that, it's not gonna be able to get that inflection. But if you say, I like this movie, and then a few seconds later say psych, the machine or the AI would pick up when psych is used in a sentence. It would know how similar psych is to all these other words. When is psych used in a sentence, and then know that you are being sarcastic, that you are being facetious, and completely negate that response and say, okay, well, even though she said, I like this movie, she didn't really like it like that. That like in that sentence, if it were to look at the embedding, that like would not be similar to love, because psych was at the end. Like would then be its inverse, right? Or I disliked, if psych is following. And so you can kind of see this mental process of how a machine may go through its motions in embedding and understanding the similarity scores between these sentences. And so there's a lot to unpack there. There's a lot to unpack with these AI models, but that is it for today. That we're about 26 minutes. We're keeping it short, keeping it sweet. Next week, we will be going on to, what are we doing next week or next stream? We're doing what is attention in language models. Attention, something I was never really good at in school, paying attention, but now I do. And this is going to be super interesting, super interesting. Well, I thank you for joining us today. Till next time.